Good afternoon. I would like to welcome everybody on today's webinar. This is part of a session of webinars organized in relation to the release of ConSteel 11. This webinar will consist of two parts. The first part of the webinar will speak about modeling of frame corners. And the second part will speak about the use of shear field objects in structures, mainly in industrial type of buildings. My name is Bálint Vaszilievich Semjen. I'm a Senior Development Engineer at ConSteel Solutions Kft. And we will use for this presentation a system which is probably already known by those who have seen already such webinars. You see on your screen a control where with the red button, red arrow which is marked, you can hide this panel if it disturbs your view on the screen. And if you may want to ask a question, then you can type into the field which is shown by the arrow at the bottom. You cannot ask questions by voice. You are muted. You can only type the question if you have. I will try, depending on how quickly we will finish this webinar, which is planned to last 1 hour. If we have time at the end, then I will try to answer your questions which you may have. In case we don't finish in time or you have questions later on, you can reach us using the usual communication channels and we will answer your questions as soon as possible. So the first part of the presentation will be about modeling of corners, moment-bearing corners of structures built with bar elements in ConSteel. In the first part, I will speak a bit about what similar functions already exist in ConSteel 10, previous version. Then I will show the type of connections which exist in the new version ConSteel 11, and then I will show how to use it in practice for the analysis of structures built from bar elements. In ConSteel 10, we already implemented a tool which is called Corner Wizard, which allows parts of the structure to be handled differently. Differently means that the user has the chance to separate parts which he believes that are not acting as beam elements because they are within a region, a corner region. Within a corner region, those bar type of displacements and as a consequence those bar type of internal forces are most probably not valid anymore. It's much more precise to say that this region is excluded from a bar-based analysis and then the region itself in its full 2D or 3D extent is modeled with an appropriate way. ConSteel contains the CS joint software which is able to analyze such a corner region with all the required components like shear buckling of the web panel, effect of compression force on different parts, and also the flexibility of end plate connection. So, but also other methods can also be used. This is a choice of the engineer. The engineer may decide to continue to verify these elements as bar elements. In this case, obviously, he will get slightly higher bending moments and also shear forces, which are calculated at the intersection of the reference line of the bar members, or when he wants, then he can switch on the corners. In this case, those sections of finite elements which are inside the region are excluded, and then the connection itself must be checked separately. In ConSteel 10, it was possible to define only one type of connection. This type of connection was a sort of generic moment-bearing connection of undefined topology. It was just a connection which means a moment-bearing transition of internal forces, bending moments from one element to another. When such a connection was switched on, then the finite elements within this zone were disregarded for the internal force calculation and displacement, were also excluded from the critical multiplier calculation, as a consequence also from the stability calculations, and also additional also in the plastic analysis. These sections were not considered these parts of the connection. Based on our long time experience, the use of such generic without precise topology type of connection gives a realistically good result, although, as you will see in this presentation, certain type of connections show surprisingly different behavior when they transfer a torsion effect which appears on one end, one member of a corner, and then how this torsion is transferred to another member. The implemented generic connection type works based on analogy with the traditional 6 degrees of freedom. It results that the B moment, which is the internal force belonging to the 7th degree of freedom, the B moment will be equal in a corner if there are only 2 elements connected to each other, like visible on the screen. In ConSteel 11, we extend the present possibility of generic connection by 3 more specific type of connections. As you can see on the right side, it is shown with the beam and the column elements just touching each other at the corner of the reference axis without forming any sort of physical connection, without any representation of the connection, how it would look like in reality. This is just to show that this is a generic connection without any more information about how the connection itself is made. And now on the left side, you can see the 3 new types of connections where there is always a real geometry, a real topology assigned to the connection. These all 3 are still moment-bearing connections. Regarding the traditional 6 degrees of freedom, they transfer the same amount of internal force if the connection is considered as rigid, or if it's not rigid, then in function of the flexibility of the connection. Difference will be when we speak about the transfer of the 7th degree freedom displacements due to torsion. The first connection we call later in this presentation also in the software as box. In that case, the upper and bottom flanges of the beam and columns connected to each other are continued into the other element, and they form a framing around the web panel in the corner. This framing looks like a box, and we call this connection as box. And in the software, this will be marked with colors, with yellow colors as shown below. The next type of connection is called diagonal. Here in this case, the beam and column elements are connected through each other through a diagonally placed connection plate without the extended flange and beam and column flanges. And the third is a combination of the first 2, connection through the elements. Connection of the elements is through the diagonal plate, but the stiffeners are the flanges are continued the stiffeners, forming a framing around the corner web panel. All these 3 type of new connections have different colors and different symbols to show clearly what sort of connection has been placed in the model. Just to give an idea how different behavior they represent when they transfer torsion type of action, I will show a small video, a small animation. You can see on the picture 2 corners that are horizontally placed in the model. They are the same, the only difference is the topology of the connection. The first is a box type of connection with the flanges continued into the corner zone, and the other is a connection which we call diagonal, where the elements are connected through a diagonally placed connection plate. In both models, we apply a set of concentrated forces forming a torsional moment at one of the ends, and we will observe what kind of rotations appear on the other unloaded end of this structure. Now if I start this animation and just look the other end, you can see that the right side rotates in the same direction. Obviously this is how we applied the torsional moment, but you should better look to the left side, left end of both L-shaped constructions. I start again and you will see that the upper one and the bottom one rotates in the different direction, the unloaded end. The magnitude of rotations is different because it depends on the stiffness of the construction. This is not the same as visible. It's not intended to be of same stiffness. The intention of this demonstration is only to show the direction of the rotation. So the above case gives a rotation of the same magnitude of the opposite direction, and the bottom gives a rotation of the same magnitude but in the same direction. So this is a very special difference due to the topography of the connection from the same type of action appearing on one end. The other end, if it is unloaded, the other end will have a completely opposite behavior. This sort of function is now included with the use of constrained finite elements into the ConSteel model, and therefore once the engineer has decided which sort of topology he wants to assign to a certain connection, then the software will, as an additional information to the existing set of information, will know also what sort of rule this connection is forcing to the element, what is the way how the 7 degree of freedom must be transferred from one element to another element. This approach, which is summarized in this table, has been published by several researchers. One of the most famous, most well-known is a professor called Basaria, who made several studies in this subject. As a summary, sorry, I forgot to speak about the third connection. I go back just for the clearer picture because there is no animation for that. This is the third one, which is called box diagonal. The box diagonal, as I said, is basically it's a mix of the first two cases. It gives a similar way of deformation like a box, but being much more rigid. The additional diagonal stiffener doesn't allow the web, the corner itself, to distort, and therefore it is completely unable to transfer any sort of kinematic displacement of same sign or reverse sign to the other element. It will act as a sort of warping support. It will dissipate, or it will stop the warping effect to be transferred from one element to another. There is no video because there is no any such clearly visible behavior, but in this table this is also included. So the first one is the box connection. We don't make any difference if, sorry, the first is the diagonal connection. We don't make any difference if the connection is welded or bolted. We assume that if it's bolted, then there are enough number of bolts placed between the elements to ensure that the plates will firmly move together. Therefore, we don't make any difference between the way how the elements are connected. The diagonal place connection provides a full warping transfer, which means that the warping, the 7 degree freedom displacement of one end will be equal to the displacement on the other end, and it is direct, which means that it will keep the same sign. The bolted connection, the box connection, is also a full warping transfer connection. It means that it transfers the same magnitude of displacement, but it will reverse the sign, and this is an indirect transfer. The diagonal place connection acts as a warping rigid connection. It is also equivalent like if the user today with ConSteel 10 would have placed a warping support, an external warping support to a corner. The result is the same. The warping effect, which appears on one end, will not go through the connection to the other element, but it will go into the support. Mathematically, we are using constrained finite elements. constraints are, in case of a simple corner consisting of one column and one beam, is basically an equation like you can see below. K1 type phi A, so first derivative of the phi A, which is the 7-degree freedom deformation, plus K2 times this deformation at the other end will be equal to 0, and in the first case the values of the K1 and K2 are 1 and -1. In case of box type connection, both are 1. This is just the mathematics behind, and the user will just see that these deformations will appear as expected. As reference, the most obvious way to use are shell elements. As you know, in ConSteel, it is also possible not to use bar elements, but also shell elements. Therefore, I built frames first, where you can see only the corners of the frames, and I show how for the 3 different type of connection, the first eigenvalue of a frame would look like. And then after I show that we get similar results with beam elements, keeping the same special differences between the type of connection. The first one, as you can see, is a box connection. The second is a diagonal. The third is a box diagonal. Now, if I start the first one, just look, please, the direction, how the elements are moving. You may be able to see that the bottom of the beam and the inside flange of the column are both coming towards me. So they rotate in the same direction. If you look to the other picture, then you can see that just the opposite happens. The beam comes towards me, but the column goes into the opposite direction. Now, if I look to the third one, as I said at the beginning, there is not so much visible difference. The displacements are in the first case. Here you will not see the difference in magnitude because the animation is scaled to have visible deformations. Therefore, you will not see the difference in magnitude, but is transferred. So the most important thing is the difference between the first two. In the first case, both structures rotate in the same direction. In the second, they rotate into the opposite direction. As I said, I will show in the use of in the application part of this presentation how the same frame can be modeled with bar elements. But before showing how to use the bar elements, I quickly explain how this definition can be made to the bar element build model. We extend the functionality of the existing corner wizard. As I said at the beginning of this presentation, the corner wizard was used to place this sort of generic undefined topology based connection. Now we extend the functionality of this wizard, and we can define all the 3 new type of connections additionally to the existing old type of connection. In order to give the chance to use different type of connections within the same model, we use as grouping the already known model portions. Different type of structures, components, beams, columns can be placed into model portions, and then when a model portion is selected and the type of connection is selected, then there will be an automatism running behind. It will check whether whether between elements included in the selected model portion, the selected type of connection can be placed or not. There are criteria when the connection can be placed. These criteria are that the elements which are connected must have a moment-bearing connection between each other. It means that the degrees of freedom of the selected element must be continuous. They must both have eye sections. It can be welded or hot rolled. Their web must be located in the same plane, and the angle formed between the two members must fall within the range of 90 degrees plus minus 30 degrees. So these are the conditions. If these conditions apply, then the software will place a box, a rectangle with the selected color, as I will show you at the connection, to clearly show what sort of connection was applied to which collection of elements. A small summary of what is happening mathematically. In case of the dipole connection type, there is no any special name. This is the generic connection, and the 7-degree displacements are transferred, as I said at the beginning, based on the same way as for the traditional 6 degrees of freedom, without considering any special behavior of the connection, simply because nothing was defined. For the 3 first, this additional information is known, and this additional information is enforced through constraints between the connecting elements, resulting the displacement similar to what can be obtained with shell elements. On this picture at the bottom you can see some sort of a summary of articles which were used for the implementation of this function to ConSteel 11. And now I will show how the same frame, but using with beam elements, can be defined, and how the different connection I start ConSteel 11, and I will load the prepared models. So as you can see, this is a traditional frame. I used tapered columns and rafters. I used purlins as lateral supports, mainly on the upper flange, but at certain locations also at the bottom flange. And as you can see now, at the corner regions, there are such green or such green type of colors. As I said, the definition requires a model portion to be made. Now I made a model portion which includes all the 4 primary members, because I would like to place corners between the columns and the beams. I need to remember that there are certain criteria where the connection will be placed. It must both members connected to each other must be I-sections, the web must be located in the same plane, and the angle between them must fall between the 90 degrees plus minus 30 degrees. This will be valid for the column beam corners, and it will be invalid for the peak. I don't want to create such a connection at the peak. This behavior is clearly for those parts where the angle is close to 90 degrees. Okay, so my definition will be fine. In order to physically execute the definition, I go to Frame Corner Wizard, and you can see now this new window which was already shown in my presentation. There is at the bottom a switch on-off toggle where you can switch off the definition of any sort of connection. If I switch off, then there will be no any corner applied of any kind. It means that now if I run the calculations, then the elements, the finite elements which fall within the boundary of the corner zone will not be excluded from those different verifications, analyses. As I said at the beginning, we will ConSteel will consider the bending moments which appear on these elements within the zone, and when one executes strength or stability calculation, then these finite elements will be considered like any other finite element which are not within the corner regions. You will get slightly higher utilization ratios because you don't take benefit of the fact that within the zones the internal forces are probably not anymore following the behavior dictated by a beam. Now if I select back on again, then visibly the different type of connections are shown. First, I need to select the model portion which I want to use as a pre-selection of my corner definition, and then I select the type of connection which I want to apply and push apply. When I push apply, you can see that now I got two yellow buttons. If I push the other one, which is for the diagonal, then I will get green boxes. If I select the red one, which is for box diagonal, then it will be red like box diagonal. Okay, so now let's select first the box type of, and when I start the calculation, and the most visible way to show the this behavior is to show the eigenform. I don't know, is it anything visible now? Can somebody please? Can you see on, sorry, there is a technical problem here. Suddenly I got the comments that probably you see not too much from what I do. Can you please answer if you see now a frame on my screen, a one-bay portal frame? I hope it's visible. Okay, so now, so this is the frame, and like if you remember at the beginning of the presentation we had, and I go back there now, we had the same frame built with shell elements. The first was the diagonal, the box. This is the sort of displacement we expect when we look to the eigenvalues. So first eigenvalues, so both elements are moving towards me. And now when I see what was the result of ConSteel, then you can see the same. Both elements are coming towards me. Now if I select the connection to the other type, to the diagonal type, and I start to analyze this again, and again I go to buckling, then you can see that now the opposite happens. The column comes towards me and the beam goes into the opposite direction. So this is a guarantee, this is a presentation how the use of this additional constraint element with the information, with the knowledge about the expected kinematic behavior of the connection, and with this information added to the stiffness matrix of the system, ConSteel is able to use this additional knowledge and enforce the connected elements to behave in accordance with the dictation of the connections. To conclude this part of the webinar, we have implemented into ConSteel a new functionality which takes into consideration the type of connection once it is known by the designer. It may easily happen that at a certain stage of the design, the designer doesn't care too much about the type of connection which he will want to use. The only information he has in his mind is that he needs a moment-bearing connection. Maybe it's even sometimes producer or erector dependent what sort of cranes, what sort of connection type they may want to use. So it may even change during later phases of design. But once this information is known, then the user using this new functionality can have more specific, more precise analysis of the type of connection. If the information is not known, it's continued safe to use the generic type of connection, but if the information is known, this is a way to give more realistic and more precise results. The method itself can be compared with finite element, with shell finite elements, as it was also shown how the shell elements within ConSteel can give comparable results. There is still, before I close this part, I would like to call your attention to something very important. In ConSteel, we continuously improve, like with this additional feature, like with the fine-tuned finite element modeling of tapered elements. For about this, I did not speak in this presentation, but this model which I have shown contains tapered elements. These changes are continuously added to the software, and additionally in ConSteel there are several automatisms which are built to help the user to analyze and evaluate the mathematical set of results. Such very useful analyzation tool is the sensitivity method, which is built in ConSteel, which based on the energy of the different eigenvalues. So the eigenvalue as a force deformation applied on the different elements can help to select the eigenvalues which are critical for certain parts of the element based on energy calculations. These calculations are automatic as a help, and usually they make decisions based on our experience and knowledge. There are usually some sort of limit values. If a certain amount of percentage of energy is below a certain limit, then we say that probably it is safe to use this one. If this limit is above the limit, then we say that probably it's unsafe to use. Now, if we make changes in the finite element calculation engine, like by adding such features which I have shown now, connections, or fine-tuning the tapered finite element models, we don't expect changes to happen in the results of first-order calculations. That is a very robust, safe, since long time used approach how to calculate first-order results. But if you think about second-order and eigenvalue calculation, then one can understand that these are highly mathematical operations, and these are usually all based on eigenvalue calculations, which may sometimes be sometimes quite sensitive to slight changes in stiffness values of a matrix. So therefore, we cannot guarantee that with additional features later on in the software will always give the same proposals, for example, for sensitivity calculation. But we always would like to call your attention that, for example, what sensitivity analysis can give is just a proposal. It's a help to the engineer. It's an intelligent guess from the software to help the engineer to decide which form to use. The user always has the right and also the responsibility to select the correct value. So now, even if by any reason a new version of ConSteel would propose another value, it's still in the hand of the user to override this proposal and select the eigenvalue, the buckling shape which he or she might feel appropriate. So don't be surprised if sometimes these automatic proposals would give different results between versions of ConSteel. The user with his engineering knowledge can always override these proposals and find the appropriate results. So this was the first part of the presentation about the corners, and I don't want to make, if you don't mind, any break now. I would like to continue into the second part of the presentation, which is about shear fields, and then we will have a So the next part of the presentation is about shear fields. Some of you may have an idea what a shear field is, or what we call a shear field in ConSteel. Some probably not. Just by looking to Hungarian engineering practice, usually in traditional engineering practice, shear fields were never considered. I will explain what is shear field, how can it be quantified, and how can be used within ConSteel 11. Shear field is a terminology used within consideration of roof panel flexibility, mainly for the design of industrial single-story or can be even multi-story buildings. The roof of such steel buildings usually consists of trapezoidal decking or sandwich panels, which are fixed to each other. So these are panels which are fixed to each other and also to the structure which is supporting it. And depending the depth of the structure and depending the shape of the corrugations, they represent different type of resistance against displacement in its own plane. Now, traditional engineering practice was to completely disregard the load bearing and stabilization effects provided by roof elements. Roof elements are typically just designed to transfer the vertical loads to the underlying supporting structures like snow load, wind load, and such. And of course, the engineer is aware that something is still in the structure, but usually it's only considered with its load, so with its self-weight as a load increase, and it's not considered its stiffness as something which would help the structure to resist the external loads. Usually engineering practice assumes that the disregarding such elements would result in design on the safe side. There is a certain undefined amount of additional safety associated with the neglection of these elements. It's not necessarily always true. For example, if one wants to calculate dynamic calculations for seismic analysis or any sort of dynamic calculation, it is well known that a structure where, for example, there are internal and intermediate frames, and there are also end walls type of structures which are anyway stabilized by wall panels. Now, if I calculate an internal frame independent from the fact that the roof would anyway connect it somehow to the much more rigid sidewalls, then I will come to the conclusion that my structure has a relatively high period of vibration. As a consequence of that, my seismic force will be relatively small. Now, if I don't disregard the roof panel, just consider in my design, even on a safe way with a reduced amount of rigidity, with that it would give additional stiffness to the frame, the period of vibration would decrease, and the load acting, the seismic force calculated through a modal response spectrum analysis or even just on a simplified way, because of the smaller period of vibration, the force would be bigger. So now in this case, disregarding the roof panel, it's difficult to say that would result a design of the same side. But mostly general engineering practice still today is to disregard the panels, but now we added some mathematical tools into ConSteel which allows the effect to be considered for the design. It's important to note that such sort of mathematical model is only applicable for beam elements with 7 degrees of freedom. So it's only ConSteel or some other softwares which would use also 7 degrees of freedom bar elements. Only such softwares are able to mathematically consider this effect. Software which use traditional 6 degrees of freedom are unable to capture this sort of effect what is provided by the sheeting. So this is something very unique and special to ConSteel and similar softwares. The representation of the so if I connect a trapezoid decking with the underlying structure together, then obviously if there are loads acting on this, almost like a flexible diaphragm, if there are loads acting on this diaphragm, then the displacement of the trapezoid decking and the underlying structure will be combined. They will move together. So obviously the unwillingness of the roof panel to deform will stabilize the underlying structure and will limit its displacement. Typical loads which are acting on such a roof diaphragm, or in German language this is called Schubfeld, are wind loads acting on structures or stabilization loads due to the indirect stabilization provided by the sheeting simply from the connection between the two. This is actually the most commonly used application of the trapezoid sheeting, and this is also included in Eurocode 3. I will show where. So with the help of the existing roof sheeting, we can provide stabilization help to the underlying structures when they would lose stability, mainly lateral torsion and buckling. The expression of the resistance of the sheeting against shear deformation is expressed with an S value, which has a kilonewton value. There are two typical applications of such trapezoid decking. One is if I have a structure where we have frames and purlins on it at a certain distance, and on top of the purlins there is a trapezoid decking or sandwich panel where the ribs are running parallel to the roof slope, so perpendicular to the purlin. Then I can assume that the roof sheeting, when it is correctly built, erected and fixed at certain positions, then it provides an elastic restraint to the top flange of the purlin. Similar configuration can be if I have a building where there are no purlins, it's a purlin-free structure. In that case, there are high trapezoid decking spanning between frames, and then in that case, this high trapezoid decking provides similar effect than in the first case to the purlins. The upper flange of my rafters can be assumed to be elastically stabilized by the presence of this high trapezoid decking. This can ensure an economic design by considering the stabilization effect of something which by traditional design was usually not considered. As you will see in the calculation, if a shear field is appropriately built, it has surprisingly high stabilization effect, which is usually disregarded. In order to measure the specific S value of a shear field, there are several methods available. The first one is not very well applicable for engineering day-to-day practice. This is when in a laboratorium tests this shear stiffness is defined. Usually, like always in such case, one places a certain amount of load and measures the displacement. The second approach, which is already applicable for everyday design, is to use formulas included in Eurocode. The formulas are pretty complicated, so although they are existing, it's not an easy task to work through the calculation and come to a usable value. But of course, there are several small softwares or others to calculate it. And then the most common way of doing it, especially in Germany, where the whole method in everyday practice comes from, is to use tables provided by producers. In Germany, for each panel which is released for normal uses in construction business, there are certain approval documents compulsorily needed. These are called Zulassung, and in these documents, when these Zulassungs are for panels, there is always a compulsory part about shear field design, and those documents provide all the necessary parameters which were either based on laboratory tests or by calculations, but those are values which are already directly usable for the practicing engineer, and with the help of these values, the calculation itself is relatively simple. We implemented into Eurocode, of course not the laboratory tests, but we can calculate for selected type of panels the Eurocode based S value, or for German panels where the values are existing, also the S value based on these parameters. We have added a new database to ConSteel, which contains trapezoidal decking of several producers, and by selecting such panels, this S value can be calculated by ConSteel and considered later on in the analysis. The value of this S depends on many different factors, mainly on the resistance against profile distortion, which is, of course, it's important what is the shape of the trapezoidal decking. Deeper, so if the profile depth comes bigger and bigger, the profile gets weaker and weaker against profile distortion. If the profile depth is small, gets more and more close to a completely flat plate, then the profile distortion will be infinitely or close to infinitely high. Of course, this depends also on the thickness of the plate, but also depends on many other parameters, like if I have panels of a certain size and I need to connect these panels to each other to form a continuum shear field, then of course it will be very important how the connection between the elements parallel to the ribs, perpendicular to the ribs is made, what sort of connectors I use, what is the distance between the connectors, how do I fix then all these built continuum to the superstructure, do I use screws at every rib or only at every second rib, and in the latest German Zulassungs, even the number of intermediate supports, which results basically a beam on continuous support when we speak about the statical system of the trapezoidal decking. So how many such intermediate supports exist? This also has an influence on the strength of the sheeting. So the work is to calculate the S value and then use it for design. But before we continue, it's very important to understand that we are now contributing design parameter to an element which is usually not assumed to be a design as a load-bearing element. In Eurocode 313, paragraph 2.6, there is a clause about structural classes, and here you can see that there are three classes, class 1, class 2, and class 3. Class 1, it's specifically about the role of code form elements within the global structural model. Class 1 means that the constructions where code form members and sheetings are designed to contribute to the overall strength and stability of a structure. So it means that basically secondary structures behave like primary structures. So they must play the same role as primary structure. This is usually not the case unless somebody builds a structure purely from secondary elements. The second class is when constructions where code form members and sheetings are designed to contribute to the strength and stability of individual structural elements. Contribute means that it's not the main load-bearing element, but its stiffness is added and the structures work and play together. So this is exactly this field when I said that the sheeting itself contributes to the stabilization of the upper flange of a purlin, or the high corrugated trapezoidal decking contributes to the stabilization of the upper flange of the rafter. The third class is basically the traditional approach when constructions where code form sheeting is used as an element that only transfers load to the structure. This is when we disregard its stiffness, it's only a weight and the load and the load transferring mean. So usually class 2 is what we need to consider. Also about how shear fields are made. So that's one thing that we calculate in S value, but as I have shown that there are certain factors which influence the value itself, plus there are also constructive detailing rules. The concept itself comes mainly from Germany, where there is a very strict approach. In Germany, a shear field requires that the boundary of the shear field on all four edges must be formed in an appropriate way. It requires connectors, direct connection of the shear field, the panel, to the underlying structure. Now, connection, if we look the supports perpendicular to the load-bearing direction, it's obviously that they are connected to those beams. So in case of a purlin system, of course, that the trapezoid decking is connected to each row of purlin. But the German approach also requires that additionally to the purlins, also in perpendicular direction along the length of the panel, there should be a load-bearing element to which the panel is at certain distances would be connected. This is not necessarily so easy. Usually this requires additional structural elements to be placed within the building and additional connector elements to be used. As you will see in the calculation example, and as I have already said, the stabilization effect provided by such sheeting is shear field is relatively high, and on other side the formation of a shear field requires some rules to be fulfilled. Also such rule is, for example, that it's not allowed to make openings in the roof, or at least very limited amount of openings, in order to ensure the flexible diaphragm behavior to be as a realistic assumption. So as a consequence of two sides, pro and contra, very often not the whole roof of a building is formed as a roof, as a shear field, but only parts of it. Very common, for example, to make that part of the roof which falls in the bay where anyway there are vertical bracings between columns. So if there are, typically in industrial buildings, vertical bracing on the two side walls are placed to be located within the same bay, so it's quite logical that there is anyway a roof bracing in the same bay, and additionally to the roof bracing one can form a shear field also at the same place. In this case, the strength, the stiffness of the roof bracing and the stiffness of the shear field will be added together. This is a way to improve the strength of the roof bracing and provide an additional stabilization to the whole building. In German practice, there are even such yellow stickers glued physically from the bottom of the structure to be very clear that if later on somebody wants to make modifications to this side of the structure, it must be understood that this is a load-bearing part. Any modification of this part must be done only after approval from the structural engineer. It's also very important to show this information clearly in design calculation, erection drawings, to transfer this information to the owner, that differently from traditional design, usually only secondary part has been granted primary role, and therefore it's not only an aesthetic or water tightness role, but there is also a design role associated to this element. Contrary to the German practice, which requires fixation of 4 edges, Eurocode, the use of Eurocode formulas assumes only as a minimum fixation on 2 edges, so it's relatively easier to use the Eurocode type of formulas. Usually they give smaller resistances. Now, if we, as I said, in Eurocode, these shear fields are mainly used to provide, to contribute to the resistance against loss of stability in the way of a lateral torsional buckling. And then there is in Eurocode 1.3, there is a formula which you can see on the screen, which is a pretty complex formula. On the left side, we see the S value, which is the representation of the shear field S formed with the panel, with the fixation, with the number of connections, with the length. So all together has a representative value of S. And this S is compared to the right side, which are characteristic of the section. These are the warping inertia, the torsional inertia, the weak axis, the inertia for the weak axis bending, and of course section length and height. And with this complex formula, one can calculate what is the minimum value of S, which must be ensured, applied through the appropriate connectors to the beam, in order to have the chance to declare that once a panel of a certain S has been considered, it is strong enough to provide all the necessary lateral restraint in order to avoid fully the need for stability verifications. To consider this is maybe possible in the hand calculation, but this is not the way how it's done in ConSteel. In ConSteel, we directly consider the value of S within the stiffness matrices. So we calculate with the help of ConSteel the value of an S, and then this S is assigned to all the element stiffness matrices which are connected to the shear field. This way, we will continuously directly consider the effect of this S in all the calculated deformations, internal forces, and eigenvalues. Now I will show some quickly what are the different calculation methods. As I said, first I show the different calculation methods which are provided by German producers. There are three basically similar but different methods depending on when the Zulassung was made. This, like many other subjects, are continuously evolving, and the new approaches consider typically more parameters in order to provide a more precise result. One of the methods which is provided by the panel producer Fischer. Wait, sorry, I deleted by mistake something which I shouldn't have deleted. Yes, so the first panel which uses the most traditional approaches from the old DIN 18807, uses only two parameters, a K1 and K2 parameter. K1 parameter is independent from the length of the shear field as formed, which is maximum, of course, the length of the roof or less, depending on which part of the roof has been formed as a shear field, and the other parameter is divided by the length of the shear field. So with these two values for each length of diaphragm, for each type of panel, the S value can be calculated. For each panels produced by Hösch, for different shapes and thicknesses, there are K1 and K2 values defined in the table in the Zulassung. The other producer, called Fischer, is already using a more fine-tuned formula. Instead of the existing K1 and K2, there are additional K1 star and K2 star constants, which consider the distance between fixations lengthwise. So what is the flexibility of the connection between the two elements? Of course, if the connection is not fully perfect between two panels, then the overall flexibility of the system made of several panels will be less than if it was just one big panel. The third approach is by Arcelor. This is the most complicated. As you can see, there are even further parameters where we can consider only the number of splices lengthwise, and also the number of intermediate supports lengthwise in the calculation of S. So these are the three different formulas provided by German producers, and then there is also a formula provided by Eurocode 3, which looks quite different. As I said, this only requires fixation on 4 edges. The first 3 German methods require fixation on all 4 edges around the shear field. And this is the Eurocode value. Now, if I start ConSteel, if I select ConSteel and I just start a small beam, and this is just to show that, let's say we have a roof which is 25 meters long, and on this roof we have a Hösch panel, a deep corrugated Hösch panel with this shape, as you can see on the picture. At the bottom I have an extraction of such a typical German Zulassung document. You can see for each thicknesses we have in the table definition for a value for K1 and K2 values for this panel with a thickness of 0.75 millimeter with positive location. These are the values which are given in the table. Now if I would like to place such a shear field on a beam, I'll show how to do it. First, let's start with a normal 6 meter long beam when there is nothing on it except a load on the top flange, and there is no any contribution from any shear field assigned to it. Now if I calculate the critical buckling value, then we can see that this is 4.14. It's a relatively low value. It's an unstabilized, it's a freestanding, simply supported beam. Now if I would like to consider the contribution of a roof sheeting, then there is a new function here in ConSteel. You can see it forms a trapezoidal decking. By selecting it, you get this screen where you can define a new shear field object. You can give a name, and from this bottom, as I said, we added a database of different panels. You can see the different most common German producers. The first 3 German producers have all its own specific calculation methods which are specific to the panel. The last 2, Lindenberg-Pruszynski, don't have such values. Such panels can also only be calculated with the Eurocode formula. Of course, all the German panels can also be calculated with the Eurocode formula, so it gives a chance to compare the values. Don't be surprised that there might be quite different in different cases, but also don't forget the German approach assumes support on 4 edges. Eurocode assumes only on 2 edges. So now if I select the Hirsch panel, positive 135, 0.75, and then I say load, then the panel will be loaded into the screen. And then when I select the panel itself, then we can see that we need to define the length of the shear panel. As I said, this is the length of the shear field, which is formed as a shear field. It's maximum the length of the physical length of the building. Let's say in this case the whole 25 meter is formed as a shear field. So I define 25, and I see that now I receive 4053 kilonewton per meter value. And now when I place this panel on the structure, I select shear field 2, I see again the 4053 kilonewton per meter value, and I still need to give what is the effective width of the panel. So what is the length of this panel of the shear field which contributes to this element. Now in my case, let's assume that we have 5 meter distance between my rafters, so I give as effective width A equal 5. This A goes into the formulas of the German formulas like A. So the S, the total S, will be the tabulated value multiplied by the physical distance between the elements. Total will be 4,000 times 5, so it's 20,000 kilonewton. It seems to be a huge number. Additionally to the definition of S, I need to give also where is physically connected the panel to the element. I say top middle, select the beam, and if I select top middle to the beam, then you can see that the software has shown a sort of symbolic symbol for the presence and also the physical location of the trapezoidal decking. Now if I start my calculation again, remember it was 4.14, and 4.14 will drastically increase to almost 100. So it means that by the application of a shear field panel, it's a 135 millimeter deep corrugated panel, it has caused an increase of a factor of 25 if we speak about lateral torsion and buckling related first angle value, which is of course a drastic value. Now we may say that, and as I said anyway, it's probably quite restrictive to try to make the whole roof of the building as a shear field. It's probably well enough to say that, let's say we will use only 5 meter of the roof as shear field, and we will contribute this 5 meter length shear field as a stabilization to all the rafters of the building. So in that case, I come back to the definition and I change the 25 to 5 only. So the shear field itself will have a length of 5 meters only. As you can see, the 4,000 got dropped to 900. And of course, it doesn't change, it doesn't change anything. The distance between the elements is still 5. Finally, the S will not be 20,000, but it will only be something like 4,500. Still remains on the top flange. Now if I calculate, instead of 95, the value will drop to 27. The 27 is still about six times higher than the very first value of a beam without any contribution from the roof panel. So as you can see, the panel itself can be chosen from a database. We can calculate the S value automatically with ConSteel, and we don't need to make a comparison between the S and the calculated value like proposed by Eurocode, but this S value can be automatically considered within the stiffness matrix during calculation, and we will see directly the consequence of this S there. It has an effect on the calculated deformation, and it has also an effect on the calculated eigenvalues. Now I would like to go back and conclude this the webinar. So as I have shown, the function itself, the shear field, can be assigned to a selected element by calculating or specifying manually an S value. You can even define any sort of value manually without the calculation executed by ConSteel. So we need to specify an S value, and then we need to specify the eccentricity of the panel relative to the beam element. It can be top flange, bottom flange. It's usually placed on the top flange in most common way. There is one very important side remark. As I said at the very beginning, in Europe, based on our knowledge, the strongest engineering practice for such elements is in Germany, where traditionally such beam elements are designed individually, excluded from the global model as 2D elements, and then on these 2D elements, using special softwares with 7 degrees of freedom for bars only, they place this S value specifically on these two-dimensional beams. Now, Eurocode ConSteel is a 3D software, and we extended the applicability of the shear field elements to a 3D model, but don't forget that physically these are always still connected to one single element. So even if I said at the beginning that it looks like a sort of flexible diaphragm, it doesn't have a real 2D continuum. It cannot force different pieces, different bars of a roof to move together. These are always just assigned as a lateral spring-like element to a specific selected beam, and it will provide contribution only to this specific beam. There is no any automatic connection through the application of the shear field object between the elements which are located in the same roof plane. The shear field itself will always provide an effect which is perpendicular to the original longitudinal reference line of the beam. So it will be always a sort of out-of-plane effect, and it will keep this direction through the displacements in the model. If somebody wants to build a 3D model by considering a shear field at the same time on both on purlins and rafters, or so in 2D elements perpendicular to each other, then special care must be done, and the results must be carefully analyzed to see if they can be still considered as realistic or not. And there is also one important remark, is that although ConSteel calculates the S value and considers it in the final element design, of course, there must be appropriate connectors between the substructure, the underlying substructure, and the sheeting. The calculation of such forces which are between these elements are not covered by the present version of ConSteel 11. So if somebody wants to consider such elements in a real design, then should not forget that there is this additional task remaining to estimate these forces and select the appropriate connectors. Usually, and I call to the application of German panels, usually there are very well documented application rules and practical rules described in these documents how to place the connectors at which distances in order to ensure a continuous, strong diaphragm as needed. Okay, so that was for shear field, and with this I would also finish my part. We run out a bit of the time, but if somebody may have some very quick question, then I would be glad to answer. Or if the questions are more complex or complicated, as I said at the beginning, through the well-known channels, we can answer all the questions you may have. I would finish my webinar for today. Thank you very much for your attention. This webinar will be recorded and be available on our YouTube site like all the previous webinars. So you are also welcome to review all the previous webinars, or later on can be also seen again if something was not clear or somebody may have missed some parts of the presentation. Thank you very much for your attention, and I wish a good afternoon. Bye-bye.